we're here in your new lab. We've got your lab set up. What are some of the experiments that you're working on right now?
Trying to energize the Earth and see if I can get levitation off the ground just from negative charge, charging up the ground. I want to see how much of an electric field I can generate above the ground in volts per meter. Supposedly there's 100 to 300 volts per meter just because the air and the Earth. And I want to see how much we can amplify that, and if that has anything to do with Alexei's graviflyer or any of these other Kium tricks that we're seeing lately.
Okay, actually that's a really interesting idea. So what you showed me a few minutes ago, if I could describe that, basically you had an aluminum plate that presumably hovers over the top of the ground, and then a couple of stakes that are running current through the ground. And so this would almost just be like lens effect, right? Where you put current through the ground and you push against that.
Yeah. So really you want the voltage on the surface of the ground to be, 10, 20 kilovolts. But the problem I have is that power supply is dead, and I need to fix it.
Yeah.
So I have another one, but it's not ready to use.
Now, I've read about experiments like that in the past, and there have been different ways to apply that. I think some of this may come out of Tesla's experiments. He felt that he could transmit electricity through the air and the ground simultaneously. And then I've read something about xenic surface waves, and I'm not fully clear about that. But if I understand correctly, their idea was they wanted to use RF to do the same thing that you're doing, essentially, except they would apply that externally instead of using electrodes.
Yeah, I mean, there's ideas for reflecting it off the ground and bouncing back up, but the amount of power you need to do anything like that is megawatts if it's going to reflect it off the ground. I mean, my principle is just, Q times electric field, charge times electric field. The greater the charge I can pump into the ground, the more electric field I'm going to have to repel off of. But like this Kium box, he's got high voltage in there. There's lots of tricks you can do with high voltage and lots of charge, especially when things aren't grounded. You don't really know what's going on, and if you don't have any meters and you don't have any ground connection, it's just floating. It could be anything.
Well, so with Kium, that's something that I'm a little bit newer to. I know that like Charles Crawford, he started to get excited about that, and that's something, as you mentioned, you're working with as well. If I understand correctly, that's a gentleman in Africa, I think maybe Ghana or something like that, who has a box, and from what I've seen, there's a hole in it, and nobody's sure if it's electrical or air pressure, but he puts things over the top of this box and they fly off, right?
Yeah, I can't tell from the videos, but it looked to me like maybe in the holes of the box there were little tips of wires sticking out. Not sticking out, but like right at the tip, so that when you set something on it, possibly, the hypothesis, that those tips of the wire are transmitting charge to the object and then repelling it.
Okay. So there could be something really novel and innovative happening.
Yeah, it's just, at the kind of power levels they're using, it's just electric charge. It's just electric fields moving stuff. This isn't anti-gravity in any way.
For me, this brings up one of the big challenges of this area is there are so many scams and hoaxes and just practical jokes out there, and some are quite elaborate. I saw one where it looked like things were flying off the table, right? Kind of like the Hutchison effect videos. And I said, this is amazing. I showed it to a couple of folks. One of them came back and said, Tim, they actually bolted the furniture and the table to the ceiling and they were dropping it. And they said, here's how you can tell. When I looked, oh my God, that's exactly what they were doing. That's really elaborate, though. The average person wouldn't see that, right?
I have seen so many people over the years come out of the woodwork with free energy machines. And they're all complicated with all these gears and stuff. And every one of them is bogus. I mean, I haven't found one other than a solar panel that actually produces energy, Either they're confusing volts, like, oh, it put out more volts than it put in. Okay, it put out more amps than I put in. But none of that is power. Volts and amps can change what it's volts times amps. And you can have an unlimited combination of volts times amps that give you the same numbers.
Now, I've also heard about something called power factor and phase angle.
Right. If you're in DC, there's no waves, so there's no phase angle. It's just volts times amps because you watts. But in AC, if the volts are positive, negative, and your amps are negative, positive, you're actually putting power back into the grid.
Okay.
If the volts are positive and the amps are positive, you're pulling watts out of the grid. But if the volts are positive and the amps are 90 degrees phase shifted, there's no power. It's circulating. It's like a capacitor and an inductor. You've got one phase where the capacitor's charged, and then the capacitor discharges, and now there's current flowing through the inductor, and the inductor is charged, and then it circulates back and forth. That's circulating energy. It's zero power factor, and when you have zero power factor, you have 0 watts. But you can have, I could have a transformer, a ferroresonant transformer, where I'm putting in like 100 watts, and if somebody came across and measured the resonance on the output, it would look like 1,000 watts because I've got 1,000 volts and an amp going through that inductor. But it's not 1,000 watts, it's 0 because they're 90 degrees out of phase. And so I've already, on an APEC years ago, someone tried to show that. And I was like, it's a ferroresonant transformer.
Yeah.
You're not getting watts, you're getting volt amps.
I think that's one of the challenges of today's online environment is it has become so easy for anyone to publish online, right? Photos and video and descriptions and schematics and all of that, that you have this collection where real material is sometimes drowned out by stuff that is, maybe it's well-intentioned, it's just bad science.
Yeah, a lot of times these things are followed by the phrase, well, it's drawing power from the earth. And it's just not. It's not. So, I try to put it nicely, but every case is just bogus. I mean, free energy, you've got a star in the sky that's giving us megawatts of free energy every day.
Well, so what are you most excited about in terms of ideas or directions or paths? Because I think all of us have that, right? Like, I know it changes over time. It's just, what is kind of the idea of the month where you're like, this is the thing that I want to explore right now?
Well, Mark's doing the Alzaphon experiment. That I'm most excited about because it's actually related to anti-gravity. It's not just high voltage and electric charge. It's actually a function of gravity that, electrons spin, and we want to take advantage of that. That is a leading edge experiment technology that we're breaking through on.
Okay.
So that to me is exciting, but it's difficult. It's not going to get you a flying saucer overnight. I mean, we're still trying to prove weight loss, let alone with the amount of power it would require to lift something. And then the other thing is David Chester and I and Michael Proney have been working on a unified field theory that's kind of based on what David had done in the past, but we've directed David toward more of an engineering look at it as opposed to a theoretical look at it. And he's looked at my model. He has no arguments with the way it works, and this is the first time I've really got a PhD to look at it and give me their opinion, and everything is right in line. But like most academics, he's going down, little by little into the research, into the rabbit holes, and pulling out what he can to try to make heads or tails of it. On one hand, I think we're really close. On the other hand, I think we're going down too many rabbit holes. But that's me. I'm more of a let's get to the finish line than let's explore every avenue.
I think that goes to the heart of your model. And so one of the things that you've said to me in the past, or at least the way that I understand it, is A lot of science, most of science, is as precise and detailed as possible, right? And it's really easy to get lost in the weeds there. And so you've really developed what I think you've called an engineering model of gravity, right? Where it's really tailored towards manipulating and leveraging it rather than trying to encompass every possible experiment.
The main point is that it's not space-time curvature. And from an engineering point of view, when someone tells you, oh, we need to bend space-time, my hands are up in the air. I have no tools that work on space-time. I can't go pick up my space-time spanner wrench and use it. So I've looked at it, what does gravity do to matter? Okay. And in terms of what gravity does to matter is in a gravity well, time slows down, lengths contract, volumes contract, density increases, time slows down as the energy decreases. Those things happen to matter. So what do we have to do to matter to make it behave that way without ever talking about space-time curvature? What can we do to the subatomic and atomic particles and molecules that make up matter to make them behave like they're in a gravitational field or an anti-gravitational field? So I'm redirecting people from concentrating on the vacuum of space and what do we do with it to here's a flying saucer, how do we make it defy gravity?
Well, and damping is something you've talked about as well.
Right. In that sense, if you have a harmonic oscillator, the oscillator is going to have a wavelength and a frequency. And the effect of gravity well is to slow down the frequency and contract the wavelength. Well, this effect on a harmonic oscillator is identical to what happens if you have that harmonic oscillator and you add a small amount of damping. Exact same things happen. They're indistinguishable. So in that sense, harmonic oscillators in a gravity well are damped. And so instead of looking at it as space-time curvature, I'm looking at it from the quantum mechanics that the damping is affecting the scale, the conformal scale of atoms and molecules and subatomic particles. So if gravity is time dilation and length contraction, anti-gravity is time speeding up and length expanding. I've used this analogy in the past on Star Trek Voyager. They like to show the ship stretch off into the distance and then in a flash of light vanish. That's a realistic effect of warp drive. If you want to go faster than light, it's going to stretch into the distance. You want to go 200 times faster than light, your ship is going to expand the square root of 200. You know, so
it's not just TV magic. It's not just a theoretical, or it's an actual effect.
It's the actual effect of anti-gravity or warp drive is that matter expands and clocks run fast.
Okay.
And without those two effects, it's not anti-gravity. An electric charge isn't going to do that.
It's worth pointing out that you have put a ton of time and energy and research into your theory. I mean, you've presented this at the APEC conference several times. The amount of work that you've done and the detail and attention and care that you put into it is amazing.
I published the first paper in JBIS in 2016. I spent all of 2015 writing it.
Okay.
And it was a step up from the paper I wrote in 2001 about warp drive. And I got it published in JBIS, and they were happy to publish it. Got a lot of good reviews, a lot of good comments, no negative comments. And then I did the engineering model paper, and I presented that at the Estes Park in 2016.
Oh, okay.
And then we went, and then I did it at APEC in 2020. So it's gotten some attention.
Yeah.
And what I'm working on now is academia.edu website has a new journal out. So I'm working with David to basically rewrite the paper in a sense, so I can publish it in that journal as well. At least, knock on wood.
Well, it's intriguing to me to see all of these different approaches and backgrounds come together, and there are pluses and minuses to that, right? I think one of the challenges is that not everyone is speaking the same language, and so, like, especially with your paper, people have to come up to speed to it. It seems like that could potentially be an issue.
Well, it's the biggest hurdle I see people have is that they're so ingrained in the notion of general relativity and space-time curvature that when they read my model, they're trying to put both together.
Okay, yeah.
You know, they're saying, okay, well, how does that curve space-time? And like, space-time isn't curved. Matter has changed. It's like, there are two different interpretations. You don't want both, that's redundant.
Could you describe that as similar to Lagrange gravity, or would that not hold?
No.
Okay.
No. But it's just a matter of how do you know space-time is curved? We measure it with rulers and clocks of our choosing. How do we know it's not the rulers and clocks that are changing?
Yeah.
We don't. That's the difference in the interpretation, is that on one hand, you've got fixed rulers and clocks that don't change, measuring a space-time that changes. And on the other hand, you've got a space-time that doesn't really change, but you've got rulers and clocks that change depending on where they are in the gravitational field.
Well, it's wonderful to see innovation like this, and one of the things that strikes me about that is really modern physics as we know it is just about 100 years old, you know? And so it seems like the height of hubris to say, we've figured out everything there is to know, and this is the best way to describe it, you know? I think the reality is that the more we cross-pollinate and collaborate and bring in a diversity of ideas and people and background and education, you know, the more that we're able to understand things from a different perspective and get over some of these obstacles.
Yeah, yeah. I mean, some of the people, you know, they want to do it their way. Yeah. They want to have it this way, and I'm like, okay. But from my perspective as an engineer, this whole interpretation of space-time curvature has been holding us back for 100 years because engineers don't know what to do with it. You know, and I'm trying to give now engineers, give them a tool to say, okay, well, NMR, magnetic, you know, spin resonance, EPR, NMR, these things are the tools that we can use to control the spin, which is controlling the interaction between the vacuum and gravity and matter. And if we control the interaction and the handshake between matter and the vacuum, that's controlling gravity.
Okay, and that goes directly to Mark Sokol's work with the allosophone system.
Exactly.
So yeah, so it's controlling, in your model, it's controlling the spin. That's what controls the gravitational interaction, the coupling.
Yeah, spin isn't like a little top spinning. Spin is the vacuum fluctuation, and all fields have a fluctuation, right? The Dirac field, which controls all the fermions, electrons, protons, neutrons, all of those, they have their own zero-point field. That is the fluctuation of the field. Then the vacuum, the electromagnetic field, the gluon field, all those fields in the vacuum also have their fluctuations. And these fluctuations merge to become what we call, or what's referred to as a dissipation fluctuation theory. In that the fluctuations cause dissipation, and the fluctuations over here are a source, and they work back and forth to create an equilibrium. And everything is in equilibrium. But in a gravity well, it's not. So in a gravity well, it wants to go to equilibrium, which gives it the impetus to free fall down. Oh. It's searching for equilibrium.
Okay. And so by changing that, by changing the nature of this spin, you can decouple from gravity, and then you can get the flying saucer propulsion that Mark has been working on.
Yeah, if we can control spin, we can control which way the spinning particles want to move.
Well, and again, one of the exciting things about that is, well, for me, number one, you are both theoretical and hands-on, right? You're doing hands-on engineering work. You're taking a very detailed approach to this. But also, in terms of involvement, you have Mark, who is primarily on the builder side of things, trying to construct these, doing tests, working with material science, literally running all over the country for parts and equipment, and then you are doing engineering level work. You also have folks like Dr. David Chester who are working on, more esoteric theoretical physics, right? And so all of this is coming together.
Yeah, that's what's exciting. This is all coming together. I need Mark and these guys doing the NMR stuff and the alzaphone experiments and that to do the stuff I can't do. And David needs me to direct him toward where engineering needs to go.
You've got this team that is evolving. Where do you see things going in the near future for this?
I see that, we've got new equipment for the alzaphone experiment that Mark's getting ready. And I'm anxious to see the results of that. And for me personally, I would like to see this paper get published. And, and David too, if maybe we'll do it together. I don't know. Right now, I'm just want to get my own work out there so that more people are aware of it. Because, engineers need to be aware of what the tools are that we can use to work with gravity, where general relativity doesn't give us those tools. But I think that's about it. That's really where we're at, where we want to go with it.
I also want to ask about some of your current projects. So you're working on interferometry, right?
Yeah.
That's one of the things you're...
It's a gravity detector. So I have two. I have this one here, which I'm going to set up as an interferometer, like a Michelson-Morley interferometer. And that will allow us to do things with either the laser itself or in the path of the laser to affect the fringes and see if we can control the path of the light. And some of these tests, I really don't have the devices to say, I'm going to test this yet, but it is a way of detecting gravity. The other way I have is a laser diode that I can measure with high precision the wavelength of the laser. And if we have a test that can create length contraction or time dilation, it would affect the wavelength of that laser diode. And so I have the laser diode in a nice enclosure connected to the spectrum analyzer. So it's all one closed unit. You can measure it, and we can do things to affect that laser diode and measure how much it affects the wavelength. So these are my gravity detectors. Like I say, I don't really have the experiments set up to use them on anything, but they're there in principle for us to use when we have something.
Yeah, well, and that's building for the future, right? And again, it goes back to the collaborative nature. So not only can you use this for your material, you could theoretically use this for like experiments that Mark builds, or Charles Crawford, or the Graviflyer research that Jared Yates is doing, things like that, right? Yeah. So
now, the kind of things that'll really make these devices kick off and show an effect are large-scale, semi-explosive, kind of high energy events could show a decent signal. But the low energy events that we've been working with won't even move the needle. It's just, gravity's hard to move. It's hard to change time. It's hard to change these things. So, it'd be nice if it was the gravitational force were stronger, but it's not. It's very weak, and it takes a lot of energy to make anything happen.
Okay. Todd, thank you so much. Thank you so much for your time today.
Yeah, thanks for coming by.